Hello friends, welcome back to Webronaq. In this video, we're going to talk about one of the most important ideas in all of calculus: limits. Now the word limit sounds intimidating, but the actual idea behind it is surprisingly simple. It's basically calculus's way of asking one question: what value is a function heading toward as we get closer and closer to a specific point? That's it, that's the whole thing. And once you really get this idea, derivatives, integrals, continuity, all of it starts to make sense, because they're all built on top of limits. So let me break it down, step by step. Alright, let me show you what I mean by getting closer and closer. Imagine you're walking toward a specific point on a number line. Let's say the number 2. You start at 1.5, then you step to 1.9, then 1.99, then 1.999, and you keep going. Every step, you cut the distance in half. You're getting incredibly close to 2, but technically, you never actually land on it. Now do the same thing from the other side. Start at 2.5, then 2.1, then 2.01, then 2.001. Again, you're sneaking up on 2 from the right. So from both sides, you're closing in on the same number. And that's the whole spirit of a limit. We're not asking what is the function at this point. We're asking what value is the function heading toward as we get arbitrarily close. It's a small shift in thinking, but it's what makes calculus work. Because sometimes, the actual point itself is a problem. And that's exactly where limits become powerful. Now let's look at the example that makes limits click for almost everyone. Take this function, f of x equals x squared minus 1 divided by x minus 1. Looks innocent, right? But watch what happens when we plug in x equals 1. The top becomes 1 minus 1, which is 0. The bottom also becomes 1 minus 1, which is 0. So we get 0 divided by 0, which is undefined. The function literally breaks at x equals 1. But here's the magic. If we factor the top, x squared minus 1 becomes x minus 1 times x plus 1. And now the x minus 1 on top and bottom cancel out, leaving us with just x plus 1. So everywhere except at x equals 1, this function behaves exactly like the line x plus 1. There's just one tiny missing point, a hole in the graph right at 1, 2. Now here's the question. As x gets closer and closer to 1 from both sides, what value is the function heading toward? 2. Clearly 2. The function never actually reaches it at x equals 1, because that point doesn't exist. But the limit? The limit is 2. This is exactly the kind of situation limits were invented for. Now here's a detail that really matters. When we say x is approaching some value, let's call it a, we actually have to check both directions. You can sneak up on a from the left side, where x is slightly less than a. That's called the left-hand limit, and we write it as x approaches a from the minus side. Or you can sneak up on a from the right side, where x is slightly greater than a. That's the right-hand limit. X approaches a from the plus side. And here's the rule. For the limit to actually exist at that point, both sides have to agree on the same value. If you walk in from the left and the function is heading toward 5, and you walk in from the right and it's also heading toward 5, great, the limit is 5. But if the left side is heading toward one value, and the right side is heading toward a different value, then the function is doing two different things at that point, and we say the limit does not exist. Think of it like a WhatsApp video call. If both people show up to the same meeting, the call connects. If they show up to two different meeting links, nothing happens. Same idea here. Both sides have to land in the same place. Alright, now that we understand the idea, let's look at how mathematicians actually write this down. Because once you can read the notation, you can read any calculus textbook in the world. Here it is, the limit of f of x as x approaches a equals L. Let me unpack each piece. Lim is just short for limit. That's the operation we're performing. Underneath it, x approaches a tells you what's moving and where it's heading. So x is the variable that's sneaking toward the value a. Then f of x is just our function. The thing we're evaluating as x moves. And L on the right side is the answer. It's the value that f of x is heading toward. So if I write limit of x plus 1 as x approaches 1 equals 2, I'm saying exactly what we saw 2 frames ago. As x gets closer to 1, the function x plus 1 gets closer to 2. That's the entire sentence in math form. Pretty clean once you decode it, right? Now let's look at the cases where things don't go so smoothly, where the limit refuses to exist. Okay, so we've talked about limits that exist. But limits don't always cooperate. There are 3 classic situations where the limit just refuses to exist. And you'll run into all of them in calculus, so it's worth knowing them by name. First one, the jump. The function approaches one value from the left, and a completely different value from the right. Like we said before, the two sides disagree, so there's no single value we can call the limit. The graph literally jumps. Second one, infinite. As x gets closer to the point, the function shoots straight up, or straight down, toward infinity. There's a vertical asymptote there. The function isn't approaching any finite number, so technically, the limit doesn't exist in the normal sense. We sometimes write that the limit is infinity, but really, that's just our way of saying it's unbounded. Third one, oscillating. This one is a little weird. As x approaches the point, the function keeps swinging up and down faster and faster, never settling on a single value. The classic example is sine of 1 over x. As x approaches 0, it just refuses to commit to a value. So jump, infinite, and oscillating. If you see any of these three behaviors at a point, the limit there does not exist. Everywhere else, you're usually fine. So at this point you might be thinking, okay, limits are a neat idea, but why do we actually care? Why is this the foundation of all calculus? Here's the answer. Limits are how we make the leap from regular algebra into calculus. And the clearest example is the derivative, the slope of a curve at a single point. Now think about that for a second. Slope normally needs 2 points, right? Rise over run. But at a single point, there's no run. There's nothing to divide by. So how do we even define the slope at one point? The trick is, we cheat. We pick a second point that's close by, draw a line through both, that's called a secant line, and we measure its slope. Then we slide that second point closer, and closer, and closer. Each time, the secant line tilts a little, getting more and more aligned with the curve at our original point. And here's where the limit comes in. As that distance, we call it h, approaches 0, the secant line transforms into the tangent line. The slope of that tangent line is the derivative, the instantaneous rate of change at that exact point. That whole formula you see on screen, that's the definition of a derivative. And right there in the middle of it is a limit. Without limits, derivatives literally cannot be defined. Same goes for integrals. They're built on limits too. So when people say calculus is the math of change, what they really mean is, calculus is the math of limits. Everything else is built on top. Alright, let's wrap this up. A limit is about approaching a value, not actually arriving at it. We care about where the function is heading, as the input gets closer and closer to a specific point. For a limit to exist, both sides have to agree. The left-hand and right-hand limits must match. And we saw 3 classic cases where limits don't exist: jumps, infinite blowups, and oscillations that never settle. Most importantly, limits are not just a textbook idea. They are the engine that powers all of calculus. Every derivative, every integral, every concept of instantaneous anything, it's all built on limits. So the next time someone tells you calculus is hard, just remember, at its heart, it's really just one simple question, asked very carefully. What is this function getting close to? If this video helped clear things up, hit subscribe. We've got more calculus and computer science concepts coming up on Webronaq. I'll catch you in the next one.